ครับผมสวัสดีนะครับกลับมาพบเราสองคนอีกครั้งหนึ่งนะครับผมจากที่เมื่อวานตอนเช้าที่เราเป็นทำหน้าที่เป็นพิธีกรช่วงพิธีเปิดช่วงเช้านะครับแล้วช่วงบ่ายเราก็คือหายไปไหนเราก็ไม่รู้
ช่วงบ่ายก็แบบว่าเปลี่ยนคนครับเป็นการสลับเปลี่ยนนิดหน่อยนะครับ
ครับผมเบื้องต้นตอนนี้เราเหลือเวลาอีกประมาณ9นาทีนะครับจะเริ่มงานรายการแรกของวันนี้นะครับผมเดี๋ยวขอทบทวนนิดนึงนะครับสำหรับท่านผู้เข้าร่วมงานที่ไม่ได้มาเมื่อวานนะครับวันนี้ก็ท่านสามารถลงทะเบียนชื่อนะครับได้ที่
รับป้ายชื่อ
ครับรับป้ายชื่อแล้วก็คูปองอาหารนะครับได้ที่โต๊ะลงทะเบียนหน้าตรงโถงหน้าห้องบานเย็นนะครับห้องนี้ก็คือห้องบานเย็น
ใช่ซึ่งก็คือห้องนี้นั่นเองนะครับก็คือสามารถรับบัตรแล้วก็ลงทะเบียนได้ที่ด้านหน้าของห้องนี้เลยนะครับถ้าเกิดว่าใครที่เดินเข้ามาแล้วเนี่ยก็จะเห็นอยู่แล้วนะครับว่ามีโต๊ะลงทะเบียนอยู่ข้างหน้านั่นเองนะครับผมแล้วก็เตือนอีกครั้งนะครับก็ก่อนที่จะจากกันในวันนี้นะครับอย่าลืมคืนป้ายด้วยนะครับเพราะว่าเราจะเอาป้ายมาใช้กันต่อในปีถัดไปนะครับผม
ก็สำหรับงานในปีนี้นะครับผมเราจัดที่ตึกนี้แทนนะครับโดยปกติเราจะจัดที่ตึกมหามกุฏนะครับก็คือตึกสูงๆข้างๆนะครับแต่ว่าปีนี้เราเปลี่ยนนิดหน่อยครับมาลองใช้เป็นตึกนี้แทนนะครับ
ครับผมเพราะฉะนั้นลองใช้สถานที่
ครับผมเพราะฉะนั้นท่านที่มางาน APAM ทุกปีอยู่แล้วก็อาจจะรู้สึกว่าห้องนี้เล็กไปไหมจะจุคนได้หรือเปล่าจริงๆเรามีห้องอีกฝั่งนึงนะครับก็คือห้องบานเช้านะครับผมเพราะฉะนั้นเนี่ยก็คือท่านสามารถนั่งได้ทั้ง2ห้องเลยนะครับสำหรับกรณีที่ท่านผู้เข้าร่วมงานที่นั่งอยู่ห้องฝั่งตรงข้ามทางเราก็จะมีถ่ายทอดสดไปห้องฝั่งตรงข้ามให้นะครับ
ใช่ครับเพราะฉะนั้นเนี่ยก็อาจจะมีดีเลย์นิดนึงนะครับแต่ว่าไม่ต้องกลัวนะครับทุกท่านก็จะเหมือนกับว่าได้อยู่ในงานเดียวกันกับเรานั่นเองนะครับผมแล้วก็ทั้งนี้นะครับ
ก็สำหรับabstract แล้วก็ตารางเวลา
ครับผมตารางเวลา abstract นะครับแล้วก็ถ้าเกิดท่านไหนอยากทราบนะครับว่ามีการนำเสนอผลงานหัวข้ออะไรยังไงบ้างนะครับสามารถเข้าไปดูได้ที่เพจ Facebook APAM จุฬานะครับก็คิดว่าทุกท่านน่าจะกดติดตามอยู่แล้วนะครับเพราะฉะนั้นเนี่ยก็สามารถเข้าไปดู abstract ในงานนั้นได้เลยนะครับแล้วก็จะมีกำหนดการต่างๆนานานะครับก็อยู่ในงานนั้นเช่นเดียวกันครับผมแล้วก็สำหรับเนื่องจากว่าเรามีการย้ายตึกนะครับเพราะฉะนั้นเนี่ยที่ตึกนี้เนี่ยห้องน้ำก็จะแปลกๆนิดนึงนะครับก็คือเราจะแบ่งออกเป็นชั้นนั่นเองนะครับซึ่งชั้นเล็กขี้เนี่ยก็จะเป็นชั้นของห้องน้ำหญิงนะครับแล้วก็ชั้นเล็กคู่จะเป็นชั้นของห้องน้ำชายนะครับเพราะฉะนั้นเนี่ยถ้าเกิดว่าท่านไหนที่อยากจะเข้าห้องน้ำก็ดูเลขชั้นด้วยนิดนึงนะครับเพื่อที่จะได้ไม่เป็นการเข้าห้องน้ำผิดห้องนะครับผมแล้วก็เนื่องจากงานของเรานะครับมีการรณรงค์เรื่องการลดขยะนะครับเพราะฉะนั้นเนี่ยเราก็เลยมีการรณรงค์ให้ทุกท่านเนี่ยนำขวดน้ำกันมาเองนะครับแล้วเราก็มีจุดบริการน้ำดื่มนะครับอยู่ที่ด้านหน้าของห้องบานเย็นอยู่ตรงบริเวณโถงของห้องบานเย็นนะครับซึ่งก็คือห้องนี้แล้วก็ถ้าเกิดว่าท่านไหนที่ไปตรงห้องบานเช้านะครับก็จะเห็นว่าตรงนั้นเนี่ยก็จะมีจุดบริการน้ำดื่มด้วยเช่นกันนะครับผม
ก็ครับผมก็เดี๋ยวก็จะมีจบเซสชันแรกของเราก็จะเป็นบรรยายพิเศษจากนะครับอาจารย์professor จังเลยนะครับก็เราจะเริ่มตอนประมาณ9โมงนะครับ9นาฬิกาตรงนะครับแล้วก็หลังจากนั้นก็จะเป็นพักเบรกนะครับซึ่งอาหารว่างเนี่ยก็คือเดี๋ยวเราก็จะเตรียมไว้ที่โถงหน้าห้องบานเย็นนะครับแล้วก็ห้องบานเช้าด้วยนะครับ
ก็จุดก็เหมือนเดิมนะครับขอความร่วมมือนะครับในการงดรับประทานน้ำและเครื่องดื่มในห้องบานเย็นแห่งนี้นะครับผมก็ถ้าเกิดว่าตอนนี้ก็ยังพอมีเวลานะครับถ้าเกิดว่าท่านไหนยังแล้วก็วันนี้นะครับเรามีตลาดนัดนะครับของที่จุฬานะครับถ้าเกิดว่าท่านไหนสนใจนะครับหลังจากจบการบรรยายนี้นะครับก็สามารถที่จะไปตลาดนัดไปเดินซื้อของกินได้นะครับ
อยู่ตรงไหนครับตลาดนัดอยู่ตรงไหนครับ
อยู่ตรงข้างตรงลานตรงนั้นเรียกลานอะไรนะ
ตรงข้ามตึกเรา
ตรงข้ามตึกเราใช่ครับตรงข้ามตึกเรา
เดินออกจากตึกไปเลี้ยวซ้ายก็จะข้ามเหมือนเป็น
ใช่ครับผม
คูน้ำนะครับก็ข้ามตรงนั้นไปก็จะเห็น
จริงๆคืออยู่ข้างๆตึกจุลนะครับหรือว่าอยู่ตรงข้ามกับตึกมหามกุฏนั่นเองซึ่งเป็นตึกเก่าที่เราใช้นำเสนอผลงานกันทุกๆปีนะครับถ้าเกิดว่าเดินข้ามไปตรงนั้นเนี่ยก็จะมองเห็นได้เลยนะครับผมคนก็พลุกพล่านมากเลยทีเดียวนะครับแล้วมีอะไรให้เลือกกินหลากหลายนะครับแต่ว่าทั้งนี้ทั้งนั้นเราก็มีอาหารให้เช่นเดียวกันนะครับหลังจากจบงานนี้นะครับผม
ครับโอเค แล้วก็จริงงานนี้จริงๆทุกปีเลยแหละเราจะมีงานอีเวนต์พิเศษเวลาจัด APAM นะครับก็คืออย่างปีนี้เนี่ยก็จะมีเหมือนเป็นกิจกรรมเชิญชวนผู้เข้าร่วมงานทุกท่านนะครับถ่ายรูปคู่กับกระบอกน้ำแล้วก็แฮชแท็กว่า APAM 2025 นะครับซึ่งกิจกรรมของเราก็คือทุกท่านสามารถถ่ายรูปคู่กับขวดน้ำแล้วก็แฮชแท็กอย่างที่ว่านะครับผมแล้วก็โพสต์ลงไปใน Facebook ของท่านแล้วตั้งเป็น Public นะครับผมแล้ว
เราก็จะมีทีมงาน
คอย
สุ่มขึ้นมา
นะครับผู้ชนะที่สุ่มได้ก็จะได้รางวัลอะไรยังไม่บอกละกันครับ
ครับผมเพราะอะไรเพราะเราก็ไม่รู้เหมือนกันไม่ใช่
ครับผม
นะครับก็คิดว่าน่าจะเป็นที่ดึงดูดได้ในระดับหนึ่ง
แต่รางวัลน่าสนใจจริงๆผมเห็นแวบๆแล้วนะครับก็ตอนนี้ยังมีเวลาสามารถร่วมสนุกกันได้อยู่นะครับลองพิมพ์เข้าไปใน Facebook แล้วพิมพ์หาว่า #APAM 2025 นะครับก็จะเห็นว่า
มีอะไรหลายๆอย่างโผล่ขึ้นมา
ใช่ผู้เข้าร่วมบางท่านก็ถ่ายรูปตัวเองคู่กับกระบอกน้ำถ่ายเป็นคลิปหรือว่าหลายๆท่านก็เอาใช้ AI generate ภาพเอานะครับก็ทำได้เหมือนกันนะครับ
ใช่ครับโอเคก็ตอนนี้นะครับถ้าเกิดว่าท่านไหนพร้อมแล้วนะครับสามารถเข้ามาที่ห้องบานเย็นได้เลยนะครับเพราะว่าอีกไม่นานเราก็จะเริ่มบรรยายพิเศษแรกกันแล้วนะครับผม
ครับเชิญได้เลยครับห้องบรรยายมี2ชั้นนะครับคือชั้น1แล้วก็ชั้นข้างบนด้วยนะครับสามารถนั่งได้ทั้ง2ชั้นเลยครับชั้นข้างบนไม่ต้องกลัวว่าจะไม่เห็นนะครับนั่งหลังสุดก็ยังเห็นจอได้เหมือนกันนะครับ
ใช่ก็ถ้าท่านไหนมีเพื่อนที่ยังอยู่ข้างนอกนะครับหรือว่าไม่อยากพลาดการบรรยายพิเศษในวันนี้นะครับก็สามารถรีบเรียกเพื่อนมาได้นะครับห้องบานเย็นยังว่างอยู่นะครับแต่ว่าถ้าท่านไหนสนใจที่อยากจะไปห้องบานเช้าก็สามารถไปได้เช่นเดียวกันเรามีการถ่ายทอดสดไปเช่นเดียวกันนะครับแล้วก็
จริงๆถ้าท่านมีเพื่อนไม่สะดวกมางานในวันนี้ก็สามารถ
ดูผ่านไลฟ์ได้
ไลฟ์สดYouTube นะครับจริงๆทางเพจ APAM เดี๋ยวน่าจะโพสต์ลิงก์ YouTube แล้วนะครับผมสามารถติดตามไลฟ์สดได้เลยนะครับ
ครับผมแล้วก็ถ้ามีคำถามนะครับสามารถพิมพ์ในไลฟ์แชทได้นะครับเราก็จะมีคนถามแทนให้แต่ถ้าเกิดว่าอยู่ในห้องบานเย็นสามารถยกมือถามได้เลยนะครับเดี๋ยวจะมีคนวิ่งไมค์ไปให้นะครับผมนะครับเพื่อไม่ให้เป็นการเสียเวลานะครับก็ขอเริ่มการบรรยายพิเศษแรกของวันนี้เลยนะครับซึ่งเป็นหัวข้อเกี่ยวกับ L-function number theory and analysis นะครับโดย Associate Professor Zhang เลยเพื่อเป็นการรู้จักกับวิทยากรมากขึ้นนะครับก็เดี๋ยวกราบเรียนเชิญศาสตราจารย์ดร.รัตตินันท์ขออภัยครับศาสตราจารย์ดร.ยศนันท์วีมากนะครับขึ้นกล่าวแนะนำประวัติวิทยากรครับผมขอบ
สวัสดีครับตกลงเป็นศาสตราจารย์ดร.ยศนันท์นะครับโอเคครับ เพื่อความชัวร์โอเคนะครับก็ขอต้อนรับเข้าสู่ APAM วันที่2นะครับเช้านี้นะครับผมขออินโทรนิดนึงแล้วกันว่าทำไมถึงเป็นโปรเฟสเซอร์เล่ยจางนะครับก็คือเมื่อวันพุธที่ผ่านมาเนี่ยภาควิชาเนี่ยได้รับเกียรติจากทาง CNA นะครับก็คือ Conference in Number Theory and Application ให้จัดคอนเฟอเรนซ์ครั้งแรกที่ภาควิชานะครับซึ่งไอคอนเฟอเรนซ์เนี้ยก็คือจัดกันมาเป็นครั้งที่13แล้วแต่เป็นครั้งแรกที่มาจัดที่ภาควิชาแล้วเราก็เชิญโปรเฟสเซอร์เล่ยจางมาให้ทอล์กกับเราแล้วเราก็คิดว่าถ้ามันสามารถมี number theory ที่general audience ฟังได้แล้วก็ number theory ที่จุฬาของเราเนี่ยก็สอนพวกนี้อยู่เหมือนกันนะครับก็เลยอยากจะให้โปรเฟสเซอร์เขาลองกีฟทอล์กให้ general audience ใน APAM ดูด้วยซึ่งท่านก็เมตตาอกรีมานะครับผมขอแนะนำวิทยากรนิดนึงนะครับโปรเฟสเซอร์เล่ยจางเนี่ยนะครับก็เป็นจบปริญญาตรีนะครับจากมหาวิทยาลัยปักกิ่งนะครับคือตัวท่านเป็นคนจีนนะครับแล้วก็จบปริญญาเอกจาก University of Minnesota นะครับก็คงจะทาง Number Theory นะครับไม่ต้องสงสัยอะไรแล้วก็ท่านเริ่มทำงานที่NUS หรือ National University of Singapore เนี่ยตั้งแต่ปี 2014 จนถึงปัจจุบันนะครับปัจจุบันดำรงตำแหน่งรองศาสตราจารย์อยู่นะครับก็โดยท่านก็มีความสนใจเกี่ยวกับงานด้านวิจัยเกี่ยวกับ Langlands program automorphic form L-function representation theory นะครับซึ่งอาจารย์ในภาควิชาเราก็กำลังจะร่วมมือการทำวิจัยกับท่านอยู่นะครับแล้วก็ผมเองก็ไปวิสิตที่ NUS มาเมื่อเมษายนนี้เองนะครับโอเคครับเพื่อให้ไม่เป็นการเสียเวลานะครับวันนี้นะครับโปรเฟสเซอร์จางเล่ยแหละจะมาพูดเกี่ยวกับเรื่องของ L-function นะครับแล้วก็จะพูดถึงว่ามัน connect number theory กับ analysis ยังไงนะครับโอเคครับโอเค so we welcome Professor Zhang เลย for giving us a talk. Thank you.
Okay, thanks for the introduction. Okay, thanks for the invitation, and it's a great honor to visit Chula the first time and also give a talk in this fabulous annual meetings and conference. Okay, I learned a lot from yesterday's talk. I was going to try my best to use what I learned yesterday and try to explain today's topic. Okay, I think my original title is the L-function bridging the number theory and the analysis, but I think it's probably more suitable to change the title to bridging the pure and the applied math versus the number theory. Okay, as we know, the Gauss said the arithmetic is the queen of the math, but for me, the number theory is also the interdiscipline between the pure and the applied math. And especially in the first half of my talk, it's quite elementary. I'm going to try my best to justify this point, especially to show how historically, how do we use the computer, the computational data to help us to find the pattern of the number theory. This is a classical data-driven research. Okay, without further ado, let me start from the very simple concept, the prime number. I guess everyone knows the definition of the concept, the prime numbers, right? And this is basically the oldest topic or the concept in the human history. And I also download a picture from the Wikipedia. You can see this is probably the earliest record for the prime numbers. It's already like almost 4,000 years ago. I believe it is probably discovered much earlier than that. Even we have the way to record to the history. And here are some very simple examples. Okay. Now, I believe the prime numbers for me is not just like a mathematical concept. It's like the atom for the physics, which is what I mean by that. This is like the mathematical modeling we learned yesterday. You see, you have the problem in the real world. So the prime number is really the data we can learn from the real world, which means like I give you this 10 by 10 table, which is the first 100 natural numbers. So I just highlight all the prime numbers. I believe that without tell our student, like the elementary student or even the junior student, without telling them what's the definition of the problems, I guess they are quite easy to figure out, even just look at this data. They can quite easy to figure out what's the pattern you are trying to highlight, right? And in the other words, now we have the large language model, we have AI. I quite believe, I never tried this, but I quite believe if you have an unsupervised large language model, which is you train with like the natural number, you show the machine what is the multiplication. And this is like the alpha geometry. I guess the machine gonna discover the prime number by itself, okay? The reason is because this is same as the alpha geometry. The way they did it is just randomly, roughly say, it's just randomly draw the lines to see which one statistically, which one is going to be more helpful. But if you try with the machine, same idea for the prime numbers, you're going to see this pattern of the numbers going to play the significant roles for many, many questions. So that is very natural and very real for this world. Okay, so this is some examples. This is like the data we learned from the mathematical modeling. This is the real data we have. Now we input or we learn it. So we're trying to use the knowledge we learned to understand it. And at this point, I think it's also good to quote the Einstein's word again. What do we know about this? The knowledge is the limit, but our imagination encircles the world, which is you can ask a lot of questions, which you're gonna eventually find out only very, very little of it we can solve it. The most questions we ask, like even the elementary student can ask, is we actually have no answer, or it's very difficult. It's like Bose asked like more than 1,000 years ago. I'm gonna show you some examples. Okay, this is the first 25 primes. And now let's see how about the larger one. This is the example is on the one side is like the minimum primes. How about the larger one? Okay, so you see I write quite a big numbers here. And if you are familiar with the number series, you know this is, I'm gonna tell you the power of the two is gonna be a prime. So this is a, if you know this is so-called the Mason number. And the Mason number is roughly the prime of this form. So now question is this a Mason prime? If you put an arbitrary prime on the power, it's actually not. And back to like 200 years ago, you can publish a paper on that. Just factor through the Mason numbers. Okay, but now I'm gonna use this example to show the current limit of our computation abilities. So the answer is yes. This is the largest known this largest known prime numbers in public. Okay, of course, this is in sense of the cryptography. The larger number is also, as a public case, could be a secret for the nationality security. Okay, so this number is quite huge. It's impossible to print it. You can see there's for almost 41 million digits. And the people who cover this is primes actually using the GPU is also quite successful advertised for the NVIDIA to promote their GPU, how powerful is you can discover. And now the question is, what is the boundaries? What is the next prime? The reason we choose the Mason prime is this is to recover another question. As we know, the prime number is going to be infinite many. Okay, it's very easy to prove. And now, if you answer these very rough quantitative problems, now you can see, can we find a pattern? See, which means like, can we find a formula to predict the next primes? And the Mason number, this is a way people to try. It's not always like you're going to get a prime number easily, but statistically, or probability is quite easy to get a prime one. But again, this is kind of like intuition. It's kind of feeling. It's not a formal mathematical statement. Which means like if you want to prove the statistically, probability, you have a very high probability to get a prime number. You have to prove it, which is not easy at all. Okay, so but this is people's try to find the formula to get a more precise information, to find the patterns. Like we see, you have the tables here. It's quite messy. And what we are trying to do is using our limited knowledge, trying to approximate the truth. Okay, so let's go back. Let's see, the proof of this one is very short. And you can, this is also the first few examples we learned how to use the contradiction to prove things, right? And you also even can try, I can even make it the problem harder. Say, for example, I can make the problem more complicated. Now I have all the primes, all the primes, at least here. You use the same method. You also can separate all the prime as two parts. The one part is module 4 equal to 3. The remainder is 3. The other part is remainder equals 1. You can even use the same method to get the remainder is equal to 3. You're going to get infinity many, which is I'm going to remove the primes like 5, 13, and 17. They are the prime, which is module 4 equal to 1. The remainder is 1. Okay, this is the same method. It's like what we learned is we learn a method approach in the class, and we try an exercise, and it works very well. And you may also can try another family. Okay, how about the 4n plus 1? You know the answer could be 2, right? Either finite or infinite. Even if it's infinite, it's going to be countable. But you cannot say use the infinity minus the infinity. When we reach to the infinity minus the infinity, this is always going to be a tough question. Now, let's see, can we use the same method to do it? Unfortunately, I don't think it's going to work out, right? But how do we do it? The way to prove these two seems like play the same rule. Why the 4n plus 3 is so different with 4n plus 1? The remainder 1, the remainder negative 1, or remainder 3. Why they are so different? Why the Euclidean approach works for one well, for the others is a complete fail? It seems they should be equal to each other. This is still our kind of very rough feelings, but we still can using the data-driven, like we still can look in the data to justify our intuitions. Okay, before we do that, let's go take one step back. Let's just see how I already do know the infinity. So this is a simple property, but I want to know more precise quantitative properties, which like simple estimations. This is the prime counting function. So it's basically you input n. We counting how many primes less or equal to n. So basically, I'm going to track if the n is get larger. Do I have a reasonable estimation for the prime, for the number of the primes? Okay, you know where I'm going. I'm going to go to the distribution of the prime number, and here's our very simple examples. Like the example I show you, if you input n is 100, you're going to have 25 primes, which is exactly the table we see. And if you use a Mathematica or any software, it's very easy to check to get this counting function in our own laptop. But this is not an easy job back to like 300 years ago. Okay, so and now I just counting all the primes less than or equal to n, and I know it can be divided as two families. I'm gonna ignore the prime 2. The 2 is very special. It's the only one which is the even primes, right? Which is finite if you consider n is goes to infinity. Okay? So largely, let's focus on all the primes. We can separate as two sets. Okay, as also can track how it changes. And this is pictures I draw it by using the Mathematica and to show you the graph of the function. And this is also the one simple ideas we learned in the applied math. So if you're in the larger scale, the original is pi n is a discrete function. It's like a step functions. But in a larger scale, you see, I even just tried the 1000. You can see the graph is already become like a roughly continuous. But it's still like a sawtooth graph. So this is really what we see is the data from the real world. It's quite messy. But the graph seems not that bad, right? You already have the feelings it should satisfy certain patterns. This is like how do we discover the mathematical result of the theorems. So we try some numerical computations. We see the patterns behind this data. And we can summarize and try to get back to see if it's fitting to the real world, or it can help us to predict what happens in the future, right? Or what happened in the other cases. Okay, now let me show you the next one. This is the prime number theory. And actually, the asymptotics, the graph you see in the previous one, can be approximate by x over log x. And the x over log x is a real mathematical concept. So this is what we approximate to the real problems. Okay, and you're also going to see, if you have this asymptotic, you're also going to see the primes are going to become less common when the n is get bigger, when the x is get bigger or get larger. Okay, and the proof is very interesting. We already see the proof in yesterday Ploy's talk. And but I'm quite more interested in is how the people discover this theorem, or how to conjecture this theorem. The idea is almost the same as what I do the research today. So it's actually, the story is beginning from this table. It's almost, it's literally more than 400 years ago. So this is Napier's table. This is the logarithm table. Just input the x. You can check from the table to check the value for the logarithm functions. I'm not sure but when I was in kids in China, is like in the elementary school or the junior school, we still have to have a part of the textbook is like a booklet. Still have to learn how to read the logarithm tables. But now it's never happened because you can have the calculators. But back like 20 years ago, like 30 years ago, like the computer is not that popular. It's still very expensive. So we still have to learn how to find the logarithm values from the booklet. It's quite the ancient story. But this is same as 400 years ago. The people conjecture this prime number theorem is literally check two tables. You check the table of the prime numbers, check the table of the logarithms. They just realized, oh, this is very nice, the data fit very well. So this is a very classical data-driven research. Okay. So it's at this intersection point, it's very hard to distinguish the applied mass and the pure mass, right? Okay. So, and the proof, of course, is also very interesting. Even the hardest proof for the come up with the elementary proof approach to prove this. That the way we've discovered this pattern is quite fit to the way, especially we at the moment is the machine learning is revolutionary changing many things, and it still also can help us to do the job, like find the patterns in the data. Okay, this is the picture just to justify, give you more visual, give you a visual ideas to see how the two curves fit in well. Okay, this is only to up to the 10 to the just up to the 1 billion. It's not that big. Okay, you see they are very close to each other, but it's not that perfect. The convergence ratio is not that fast. Okay, I mean they are going to get close to each other, but not that fast. It's like up to 1 million is still quite far. Okay. Now let's go back to our original questions that I'm asking and also trying to answer. So this is still using the counting function. We know it's infinity, so we can count. If we only answer the questions like equal to infinity, it's not satisfied. We know even between the infinity, you can compare how fast it grows, or how fast it's decreasing, or how fast it's increasing, right? So this is density. The natural density is quite an efficient way to do it. If you have like the first one is counting the prime modulo 4 equal to 1, the second one is counting the prime modulo 4 equal to 3. If the first one is finite, this is definitely going to be equal to 0. So the limit is going to be meaningful. And now the point is let's go back to see the data. If I don't know the answer, but how do I guess the answer? Okay, this is like we go back to find the data, trying to find the new pattern to reinforce our understanding. We just train ourselves like a machine. Okay, so this is, I just try like not too big, just 10K. You can do this like 100 years ago, even like 200 years ago to get this data quite easy. So I just to keep it simple, I just keep the quotient. The pi 1 is referring to the number of the prime modulo 4 equal to 1, and the pi 3 is similar. So I was consider the quotient to see how far between these two set. Okay, now this is the graph. You're gonna see like less than 6,000 is quite oscillated. You don't see the pattern at all. But when you move to the later, you see it's already bounced around the 1. So if you have the data in your hand, you have a very direct feeling to guess the natural density should be equal to each other. So now you can make the conjecture the limit eventually should be more or less like 1/2 versus 1/2, right? Because this quotient, you see, this y-axis is going to be 1 eventually. And if you keep drawing this picture, you're going to see eventually this is going to be close to 1. Okay. Okay, now we can get back at least to conjecture answer for our previous questions, which is going to be infinity. Okay, and you can even get a stronger result. Okay, we're going to get the natural density is going to be 1/2. This is just confirm our intuitions. It's like the 4n plus 1 and the 4n plus 3. They just play the equal rule. There's no significant difference. They all contains the same size, same numbers of the prime. Although they are the infinity, but we know more than that. we know both of them just have the half of the primes. Okay. Okay, so now the more interesting question is how do we prove this, and why it takes so many years after we got the form plus 3 to get the form plus 1, and that is leading to another deep questions in the analysis, and I guess in the many number theory talk, especially the analytic number theory talk, it's very hard to avoid the Riemann zeta functions, right? It's kind of like the core subject in most number theory course. Okay. Okay, so this is the function, the Riemann zeta function, but I want to emphasize this is only defined for the real part of S greater than 1 because the converging issues, this is the infinity series. Okay. And how it's connected to the primes is we are actually using a very simple knowledge, the Taylor series for the fraction functions. Okay. So you actually can express the Riemann zeta function as the product over all the primes. So that is also kind of like the generative function is a very classical approach to handle the number theory questions. You packing all the information in a to generating a functions. So your properties you are looking for becomes analytical properties. Okay. And in this case, if you are looking, if you also can use this way, the alternative approach to prove there are infinitely many primes. The way you do that is say you have a product. If this product is a finite product, there is no way that if you take the S equal to 1, there is no way it's going to be divergent, right? If this is a finite product. But this formula tells you this product is going to be also equal to the sum of the reciprocals, the sum of the reciprocals of the natural numbers. And for this one, it's quite easy to, the left-hand side is very hard to estimate it, but the right-hand side is much easier. We do know these functions have a pole there, which is when you plug in S equal to 1, this will not convergent. It's going to be a increasing, it's a series, is positive atoms, the positive terms, so it's going to be like blow up very fast. Okay, so this is an alternate way. It's like we are using the, we are using like a nuclear bomb to prove a very simple statement, but the idea is very helpful. The previous approach is very hard to generalize, but this analytic approach, it can be generalized in very larger families. Okay, let me show you. And before that, but I also have to get more properties regarding these functions. So originally this function is defined for the real part of S greater than 1, so the part is I covered in the blue. And how about the part is on the left, okay, which is we covered by the pink. Okay. What happens for the other side? Okay. And what does we mean when the S is less than 1? The real part of S is less than 1. So this is another quite famous stories involved. It's the Ramanujan summations. And I have taught the calculus many years. So we also test the students for the converging series, something like the sum of the reciprocals. And if I test the students question like this, if they give me some answer like 1 billion or 1 million, something like that, I know it's answer, without a second thought, I'm going to immediately give 0. But if they give me some answer like this, and then negative numbers, I'm going to be very hesitant. I don't know how much, actually I don't know how much and which content he's trying to answer these questions. This is the drawback or the disadvantage. When you know more, you see the things very differently. So Let's see. This is the very nice example to show you what exactly mean when you have the real part of when the s is small. When your s is negative. This is actually the left-hand side is when you plug in s equal to -1. Okay. So this is involve another very important concept in the complex analysis. It's so-called the meromorphic continuation. So the idea is very simple. So we know these two functions very well, right? So this is the first one is the reciprocal of the 1 minus z. The second one is actually the Taylor expansion, but the domain is very different. For the first one, it's actually defined everywhere except the z is not equal to 1. When you have z equal to 1, it's going to have a simple pole. It's going to be a singularity point. But the second one, I'm considering this as a complex function. So my z is living in the complex plane. So this is a complex plane. And for the second one, this is like the arithmetic sequence, the geometric sequence. So it's going to be convergent when the absolute value of z is less than 1, right? So we know this. But we do know they are going to be equal to each other inside of the disk. Okay, so this is like the same equation. They give you the same thing, the same equation, but the two different expressions. The both expressions, the individual, each expression have their own advantage. Okay, for sure. But the meromorphic complex function have a very significant property, which is if the two functions agreed in a smaller open neighborhood, they're going to agree for all. Okay? So in other words, the local property is going to decide the global properties. So even very small piece of the information, if you know, you're going to know what happens for this function everywhere. Okay? So this is due to the symmetry or due to the holomorphic properties, what we have for the complex meromorphic function. And for this one, the right-hand side here, we also can call this is a meromorphic function for the meromorphic continuation for the right-hand side. The advantage for the reciprocals is the domain is much bigger on the right-hand side. So for the Taylor series like this, usually the coefficients contains a lot of other information we get from the different set. Okay? And in this case, just happened, you're going to have a closed formula for that. And the left side is tell us more basic properties for this function, for this Taylor series. So this is basically the idea how do we handle the Riemann zeta function. And even that is a key theme for my talk, which is the L-functions. Okay. Usually it's like you can use the series to define for the right half plane, but how do you break the barrier to continue to the whole complex plane? That is the central topic and our central problem, and also going to imply many things. Let's go back. So I'm going to give an alternative expression for Riemann zeta function. So this is the integral version. Okay, this is actually combined using the many transform, the Poisson summation formula. You combine everything on the right-hand side. This is the so-called the integral repetitions for the Riemann zeta function, and the right-hand side here is equal. They are equal to each other in sense of the real part of s greater than 1. But the advantage on the right-hand side here is you actually don't have converging issue at all. So in the other words, the integral you see here is although it's quite complicated. You see it's from 1 goes to infinity. It's a indefinite integral. But it's going to be absolute convergent. Where is the pole? The pole actually is already observed by these two fractions. This is exactly the term you see in the previous slides. I just using a part I just subtracted a part of the Taylor series. The originally you express the zeta as a series. So the information of the singularity information is already observed here. So once you can separate the singularity successfully, the remaining part is going to be well controlled. So this part is going to be absolute convergent, and this part is only not defined in 1 and 0. So now you have a very natural symmetry and also the nice domain. So this function is going to define everywhere except 1 and 0. That is going to be the two singularities point, two poles. Okay, this is for OS. And you also have the symmetries regarding S and 1 minus S. Regarding the real part of S is 1/2. So this is the two fundamental analytical properties, which is we call it the functional equation and the meromorphic condition. That is I'm going to repeat in the last 20 minutes. Okay. Okay, so that's the key analytics part. And now, since we're already here, it's very hard to avoid the Riemann hypothesis to see the formula we already have. So we already have a very natural extension, which is this complicated guy. Okay? And now the Riemann hypothesis is just to ask where is the zeros. We have the trivial zero is here, -1, 2, and all the negative even numbers. And because we have the functional equation, which is symmetric with respect to 1/2, so in other words, the left-hand side and the right-hand side, they are basically symmetry. You know one side, you know the other side. Only the mystical part is this vertical strip. Okay? And we already learned the zero-free regions in yesterday's talk. Okay? So basically, we know some result, but it's not all. We know an unbounded region. We only know the dark blue part, maybe zero-free. Roughly, the dark blue part is no zeros. But the point is, what happens like the point like these two right dots? Okay, the zero may happen there. Okay. And the light blue part is easier. The light blue part, you already have the Euler product. That is already guaranteed there is no zero. So the mystical part is in this white region. Okay. And this is also a very successful data-driven problem, is to search the Riemann zeros. And also the first breakthrough algorithm is given by Turing for the Turing method, to using the Turing method to find the Riemann zeros as much as possible. And now currently the bound is improved a lot, but the first thousands of the zeros is still discovered by, calculated by Turing. Okay. So that is also the very classical numerical questions in the Riemann zeta function. And the left picture is the polar coordinate. Just to see if I change the t, the imaginary part, how the complex number, how the values varied. Okay. Okay, and why is this so important? I just borrowed the Sanek's slogan, and also you see many analytical number theory results. Sometimes start with assume the Riemann hypothesis or the generalized Riemann hypothesis. You're going to get many fantastic results. And I just show you few examples, like the better estimation for the distributions, the prime distributions. Instead of using the x over log x, we also can use the Lie function. The Lie function is defined here. And you actually can answer many naive questions you asked for the prime numbers. Like how large of the gap of the two consecutive primes could be. So that's the large gap conjectures. And how small that is the twin primes conjectures. which is not directly relative to Riemann zeta, and also the Goldbach-Wick conjecture, which is all the numbers can be expressed as a sum of 3 prime numbers. So this kind of question is even you tell the kids, he can understand it quickly, even numerically check it. But it turns out it's extremely hard to prove it. So that's also the charming part of the number theory. We are all equal no matter which mathematicians, we are all equal in the front of those kind of the conjectures. We are know very little. Okay, so this is the picture I'm going to show you. I just combine all the 3 functions together. I just added one more Li, and using the same data. And you can see the approximation is already much better. So this is the second one, is the data-driven. You're going to get the better approximations. Right? The x over log x is the first version. Okay. Eventually, this is the L function is for the rank 1 L function, and the Riemann zeta is like we consider as a trivial L functions. Following these directions, eventually I'm going to end. I hope I can end at the higher rank or higher degrees of the L function to connect it more number theory or arithmetic result. Okay, so in order to generalize the Euler product, when we express the Riemann zeta function as a product of the prime, the key property we use is the arithmetic fundamental theorems, which is you can express every natural number as a product of the primes in a unique way. And so this productivity, which is the multiplicities which we want to keep. So this is the functions we introduce, just to keep this multiplicativity. And when they are prime, the m is fixed. When they are not co-prime to each other, I just input the value as 0. So I just only selected the number which is co-prime with m. And this can help us to recover the modulo, distinguish the modulo 4 equal to 1 and the negative 1. So that's the 2 functions we choose. Okay. So the first function is more or less trivial. The second is the signature function. When n is modulo 4 equal to 1, this is going to be 1. When n modulo 4 equal to negative 1, this is going to be negative 1. So this is like the indicator. We can select the correct primes and trying to generalize the Riemann zeta functions. If you are more familiar with the group theory, the finite fields, I was just talking about the multiplicative group in the concurrent class modulo 4. So you only have 2 elements here. This is give you a cyclic group, order 2 cyclic group. Okay. And now let me use the chi to replace the 1 in the Riemann zeta function. That is our Dirichlet series. And you still can have the factorization. And as a simple example, if you plot the trivial, you only remove the 1 term, the even term. So basically, you don't lose the singularity at s equal to 1, which is also fitting our intuition. You take the sum, you take the product of all the reciprocal of all the primes, you still get infinity. So that is where this pole coming from. And how that is connected with the Dirichlet function. And we need one more, the sign, which is, you see, this is pick up the prime, pick up the all the numbers, modulo 4 equal to 1 and negative 1. If modulo 4 equal to negative 1, the sign is going to be negative here. It's going to be alternative signs. Okay? And you're also going to have the product. So you're just trying to distinguish them. Okay? Distinguish the remainder modulo 4 equal to 1 or negative 1. Okay? And you also can ask the same question, what happens at value when you x plug 1? And it turns out this is no longer infinity. This is going to be conditionally convergent. This is exactly what we learned in the calculus. The Taylor series for the arctangent x, if you plug in x equal to 1 here, you're gonna get this series. So you literally know how to compute this alternative series. That exactly give you pi over 4. So that is the analytic information you have for these L functions. Now I have two L functions. And if I have these two L functions, it's going to be good enough to answer the Dirichlet, to have the Dirichlet theorem. And it is even better. This is going to be conditional convergent, breaking the mysterious vertical strips. Okay? Because you have the alternative sign, so you have a certain cancellations. It's no longer absolute convergent, but it's going to be additionally convergent. Okay? This is our original question. Okay, so this is the sum of the reciprocal. Okay, I just separated them. Okay, and I hope this is going to be infinite. This is infinite. I hope both are going to be infinite. If both of them are going to be infinite, I'm going to easily get you have infinite many of the p. Okay, actually, you're going to get more than that. So I play a simple trick to connect it to the two L functions by using the linear combination. You add these two terms together and also do the subtraction. So this is packing these two terms for the another two. Okay, so you see the sign will be changed here. So this sign is exactly the sign you see in the second L functions. Okay, so this is the two L functions. I was taking the logarithm. After taking the logarithm, I was taking the Taylor expansions for each one. And when the real part of is sufficient large, you don't have the converging issue at all. I can do whatever we want. We can do whatever we want. So the majority term, this is the two majority term, exactly what you see in the previous slides. So this is the bridge to the number theory to these analytic functions. Okay. Let's take s goes to 1. Okay. And the remaining term, you don't need to vary it at all. The remaining part is going to be convergent very well. So essentially, it's going to be equal to 0. So you're going to abstract the information on the circle part, the major terms part. Okay. And you also know these two parts is going to be convergent. They're going to give you the pi over 4. So the main information is actually get from here. So that is actually roughly the half of the log 1 over s minus 1, and which is going to give you infinity. At this moment, you at least prove both these two sum of the reciprocal going to be infinity. So this is so far, I won't say the easiest way, but it's very kind of like a nice way to prove 4n plus 1. So we get a so long detour, it's like have a 1,000 years gap. That is why it's so complicated. Although you know the answer is equal, but the proof is not seen in a different way. Okay, so now I just repeat, this is actually not exactly our natural density. This is so-called analytic density, but from the analytic density, it's quite get, with the certain techniques, it's quite easy to get the natural density, which is going to be exactly 1/2. So that is complete proof of the Dirichlet L-functions, which is also completely answer the questions we asked at the beginning, and which is as a short summary for the rank 1 L functions. The journey from the Riemann zeta to the Dirichlet, or from the prime numbers to the Dirichlet. It's going to be a more general version for original Dirichlet functions. You can consider arbitrary a and m, they are prime to each other. And you can consider the primes, you given the a and the m, you just consider either for the remainder, you consider all the prime modulo m equal to a, and you can consider this natural density. So the natural density is all of them are equal distributed. The portion is the one of the phi. The phi is the size, the Euler phi function is counting how many remainders coprime with M. In other words, the cardinality of the multiplicative group in the congruent groups. Okay. Okay, and the proof is no essential difference. The proof is if you can do one, you can do the all. Okay. Okay. I guess I still have 2 minutes. I'm gonna finish my last 10 slides for the rank 2. Okay. And for the rank 2, you know, if the expert like Yot exactly know where I'm going to go in. So this is a very popular quiz in the circulating in the Facebook or the internet. I tried when I see, but I failed. Once I reduced the equation to the cubic equations, I know this is going to be a trap there. So now you have the mathematical, you actually can try use the mathematical. It's not that hard to find the integer solutions. Okay. But you know, this is going to be strong connected to the elliptic curve. This is another quite famous examples about the data-driven, and especially more exciting part is I'm not exactly going to repeat the old stories. The two new part I want to share is the one is the data-driven part. The second part is how the machine learning to find the patterns. Okay, so this is the elliptic curve. The curve is like this. We are mostly interested A and B going to be integers. We are mostly interested in the rational solutions. Okay, and it's going to be more or less numerically. The reason is because you always, although if you look at the rational solution, it's going to be a very complex question. You have an infinite set to try. Even the mathematical or any computational programmers cannot do that. But if you change the problem to modulo P over the finite field, this is going to be to looking at the solution over the P by P lattice. So that is a very classical computational questions. You can try all the P by P remainders to get the solutions of this guy, modulo P. Okay? So this is going to be a countable number. And this number, the point is we are hoping using this finite number to recover the information of the elliptic curve. Okay? So that is the additional structure. You can define the additions on the solution of this curve. Okay? And the structure is not that hard. I mean, it's still very hard, but theoretically, it's quite well understood following many great mathematicians. It's going to be a finite generated abelian group, which means you can decompose. Okay, you can rewrite the rational point at these two parts. This is just the infinity generator, the cyclic part. This is the torsion part, which is the element with the finite order. So for the finite order part, we know very well. The difficult part is how do you know the rank of the infinite part? So which is the Z, which is the little r I highlight here. Okay, this R is the most difficult part. So which is you give me a little a, little b, which is you give me an elliptic curve. How do I compute the rank? How do I compute this R? Okay, and the one way you can do is also go back to my theme, the L functions, is basically using the solution, using the local information. The local information, I mean, you consider solution modulo P, you also can imitate the procedure we tried for the L functions to packing the information together to get the L function. And this L function is going to also have the meromorphic continuation and functional equation. Okay? And another $1 million question is a BSD conjecture, which is, this is a weak version. I don't want to show you the complete version. It's going to be extremely complicated. But for the weak version, is very simple. You just say the little r you see is equal. This is another L function. I'm using the conventional normalization. This L function is going to be symmetric with respect to s equal to 1. If you want to fit into the Riemann zeta, it's actually this one is the same as a 1/2, play the same rule as a 1/2. So this L function is going to be finite at s equal to 1 by the meromorphic continuation. And you're asking what is the order of 0. The order of 0 of this L function is equal, which is analytic rank is equal to the algebraic rank. So that's actually two things coming from totally different words. Numerically, they are equal to each other. And the BSD discovers this is actually exactly doing the computational. They are actually doing the data-oriented research. They just running the fixed conductor, fixed head of the elliptic curve, just running the thousands of elliptic curve to compare the both sides. They get predict very expressive formulas for this one. So that is how they conjecture these identities, the complete version of this identity. And the last side is for the articles in the last year for the machine learning to discover. This is so-called the Formalization's phenomenon. It's like a family of the birds is how to fly in the sky, and it's actually the unsupervised neural network. You input the data, and the trained model discovered you can naturally classify the elliptic curve as a two family. The one family is like this red one, the other is the blue one. The red one is referring to rank 1, which is r equal to 1. The blue one is rank 0, which is r equal to 0. So this is also fitting. This is discovered by the machine itself, but it's actually also a well-known conjecture given by Goldfeld, which is you have 50% of the elliptic curve, the rank is 1, the other 15 is rank equal to 0. Okay, so this is what AI, at least the sign of the large language model, to show us what they can do. And you also can from here to imagine what they can do in the future. So they actually handle the better data, especially in the large scale of the data is much better than us in certain sense. Okay, so, and the last one is another connection, which is the Fermat-Last theorem. And this is also a very popular story. The last piece is regarding the mathematical reasoning part. The previous one is mostly saying something about the computational, the data, the modeling. How do you, from the real problem to do the estimation, data-driven, and find the pattern and go back. But you know, for the math, it's not just for the computational part. You also have the mathematical reasoning part. So you may argue like how the reasoning part, how the computer help us. And this is the Kevin Bazat's project, the formalization of the Fermat-Last theorems. He got $1 million of euro to support this project. Is using the Lean, the programming prover, the theorem prover programming to formalize the Fermat-Last theorems in order the computer can help us to check, to verify the proof. There are still a lot of theoretical difficulties, especially the logic difficulty is a very tough part for this functional programming part. And they are using the Lean 4 to, this is the blueprint, is the dependency graph for the lemmas or the main result they have to finish. Okay. And let me end at this part, which is the higher degree one, which is I also discussed in my previous talk. And we talk about rank 1, rank 2, and this is also slides I showed in the last time. So this is what happens for the rank n. The rank n is referring to, this is the elliptic curve, the L functions come up from the elliptic curve for the E. So this is the extra term. So for the degree n or the rank n or rank n plus 1 is depending on convention. So this is the extra part. It also has the meromorphic continuation. It conjecturally, the Langlands predict it should also have the meromorphic continuation and the functional equation. And the result is going to be the test stone is the Riemann-Newton conjecture, the generalized Riemann-Newton conjecture, which is estimated the one variance to estimate the Fourier coefficient, the bound of the Fourier coefficients, or the Satake the bound for the local Satake parameters. This part is quite technical, but honestly, this is leading to something very cutting-edge research, especially how do we get the integral representations for this one. Okay, this question is still wide open when n is greater or equal to 5, and less or equal to, like n equal to 3 and 4, is still using a very complicated integral to express these functions. Okay, thank you very much, and sorry I was delayed a little bit. Okay, thank you.
ครับผมท่านใดมีคำถามไหมครับอีกครั้งนะครับจากผู้เข้าร่วมจากห้องบานเช้านะครับสามารถถามคำถามได้โดยการพิมพ์คำถามลงภายในช่องแชทได้เลยนะครับผม
So I do have a questions on using machine learning assistant to prove for assisting the proof is how does the framework actually working in number theory, because for example in L function in some slides some few slides before we can see the memorization, something like that, right? We will have some kind of explicit function and some kind of residual, something like that. And is it possible to like find the weak approximation first, and then after that use some machine learning to find like for example the function fitting to find like some constant to go with it, and then find the bound of the residual, something or something like that. It's does the framework actually work this way?
Yeah, I think your question is asking, say, if I have a better approximation or estimations for the L functions first, and then trying to using the numerical way to do it. Okay, yeah, of course, that's the very classical way how the people do, like in the talk you already heard, like the sum convexity, the ergodic theory. That's also the very classical ways, like people trying to do the estimations, the various type of estimations to guess the informations as gathering of the information as much as possible. To the numerical part is still is like I think the current stage is there still have a gap between the theoretical part and the numerical part. It's like how do you translate the problem in the to numerical checking in the efficient way. I think that is also engineering part is difficult. Say for example. The picture for this is also good examples when you train the data is very sensitive is what kind of the data you input. In their article they also mentioned in the original approach they actually input like the A and the B, the coefficient of the elliptic curve. The machine basically cannot find any useful information. But later, they are trying to input the Fourier coefficients, the series for the L functions, and then, which means that every elliptic curve you represent by a sequence coordinated by the primes, like the solution in the finite field. You use a sequence to replace the elliptic curve. The machine is going to find the pattern very quickly. So for the numerical part, I think it's both theoretical and engineering. It's quite difficult at this stage. You're going to have many prototype or some boundary questions is work very well, but for the research, it still probably take time. Like the alpha geometry, if you have a very finite, you have a few finite many axioms, the mathematical reasoning or the deduction is like it's for the MO problems, the machine can handle it very well. But for the research, real research problem, it still is quite messy. It's not that well defined. It's still the mathematical modeling need to help us to translate a messy question into a well-designed one. Okay, thank you.
Yeah, thank you for a very motivated presentation on the reaching the pure and applied mathematics perspective together. I learned a lot on this one. Thank you so much.
Thank you.
Hello? Okay. Thank you very much for the inspiring talk. I really like the way you introduce us to elliptic curve. I think that's the most efficient way possible. But my question is, there are many versions of L functions already, the classical one, elliptic curve one, and the higher dimensional one. What do they have in common?
If we start from the automorphic representations part, we actually all this L function is arising from the representation theoretical part. Is I think the L function we are talking about the same thing. It's not like the motivic version or the motivic version is much more complicated. But the L function I think you are talking about is same. It's for the automorphic representations. All this is governed by the Langlands program. So which is the last piece you have here, you just replace this E by automorphic representation, and replace this symmetrical M by any finite-dimensional representations of the dual group. So this is basically all the L functions we are interested. So we actually only know very small family, the functional equation and the meromorphic continuation, which is like the Langlands-Shahidi method or the Rankin-Selberg method. But beyond that, like the symmetrical nth power, we only know the algebraic version, which is due to Closier and so on. But for the general automorphic form, even for the GL2, we actually don't know the functional equation and the meromorphic continuations. Okay, so back to your questions. Yeah, they are actually all belongs to the Langlands program.
Oh, I see. And can you explain more how the coefficient appearing in the formula, how is that reflecting the representation that you replacing E? How does that relate to each other?
How to relate it to the?
Oh, I mean in Langlands program, you replace E by automorphic representation.
Oh yeah. Oh, okay.
Yeah.
That's a good question. Yes. So the E is the elliptic curve, and you have we already heard the modularities talk. So after the modularity liftings, you can get a automorphic representation pi, and the pi is like a representation over the RLs. Is a product of the infinite product over the primes. So for each prime, you only have one place, which is well understood, and those coefficients gonna appears to the representations, the local representations, very naturally. So you're gonna see that, and so the relations for that is the key point is actually I need this CP is bounded in a certain way, which is like in general in the generalized Riemannian conjecture is actually predict this CP absolute value should be 1. It's purely imaginary number. But currently, we only know this is bounded. In general, it's bounded like 1 minus something over n. That's what we know at best by using the Langlands functionality to lifting like symmetrical force power. That is the best we can do. Yeah.
I see. My last question, please. If we don't even know even meromorphic continuation of functional equation is true or not, so what can we do with that L function, like for
Oh
certainty?
yeah, this is actually a simplified version. I need to know the meromorphic continuation functional equation for all L function. Say for example, if we know for all, and we can use the converse theorem, plus the theory of the converse theorem, and then you can prove the Langlands functionality. So I just summarize the Langlands program is a huge program, especially for the classical part. It's actually the key point of the Langlands program is you have the Langlands functionality, you can lifting the automorphic representation from the GL, from any arbitrary reductive group to NNGL. But this lifting is kind of like the modularity problem. But if you use the converse theorem, the theory of the converse theorem, you actually can reduce this functionality essentially by the meromorphic continuation and the functional equation. So that's the key. So basically, if you answer these questions for all L functions, I can say you basically know everything for the Langlands program. Yeah.
That would be beautiful.
Yeah, I hope so. I hope so. We can see the result when I'm still alive.
All right, thank you very much.
Okay, so I have to thank for the very wonderful talk, and I have to clear myself a little bit that I saw Professor Zhang slide this morning. It's very surprised me that I don't know, you know, the syllabus for analytic number theory course that offer here. It is exactly kind of the same. Some student may wondering, oh, Jan Yot tell him to do. No, I'm not. I didn't tell him anything about the course that we have here at Jila. So in my analytic number theory, we begin with the L function, the prime number theorem, we prove them, and we end the course with elliptic curve and modular form. Okay, so that the analytic number theory here.
Yeah,
okay, so it's a good introduction, and it's gonna be, I'm gonna let my student watch YouTube before taking the course next semester.
Thank you. Thank you. This is our common dream.
Okay, so.
All right. So next one, we would like to invite Professor Yosana Mimar to give a gift to the speaker, please. All right, thank you so much.
ก็ถ้าใครสนใจหลักสูตรโทเอกที่ภาคเรานะครับเรามีบุ๊กมาร์คให้ด้วยนะครับก็อันนี้หัวหน้าภาคไอเดียแล้วก็หลักสูตรโทเอกร่วมกันทำนะครับ
ครับผมครับขอบคุณมากครับผมลำดับถัดไปนะครับก็จะเป็นช่วงพักเบรกนะครับผมของว่างและเครื่องดื่มนะครับเตรียมอยู่โถงด้านหน้าห้องบานเย็นนะครับผมแล้วก็มีในส่วนของหน้าห้องบานเช้าด้วยนะครับก็เราจะมีเวลาพักเบรกจนถึงประมาณ 10:30 น.นะครับแล้วลำดับถัดไปก็จะเป็น
ก็จะมีบรรยายนะครับแยกเป็น2ห้องนะครับซึ่งก็จะมีห้องบานเย็นแล้วก็ห้องบานเช้าที่อยู่อีกฝั่งหนึ่งนะครับก็ผู้ใดที่นำเสนอผลงานในช่วงเช้าอันนี้นะครับก็สามารถนำไฟล์มาลงในที่คอมพิวเตอร์ของแต่ละห้องได้เลยนะครับผมแล้วก็เมื่อจบงานการนำเสนอผลงานแบบ parallel แล้วเราจะกลับมาที่ห้องนี้อีกครั้งหนึ่งตอนเวลา 11:30 น.นะครับก็จะเป็นในส่วนของพิธีปิดนะครับผม โอเคครับผม